Hi, my name is Jason. In this video, I'll be describing a bit about a deep learning architecture known as Transformer, which was first described in the 2017 paper, Attention is All You Need. Transformer is a sequence-to-sequence model that doesn't use convolution or recurrence. The architecture has two major components, the left column, which is called the encoder, and the right column, which is the decoder. The authors originally trained it to translate from English to French and from English to German. The encoder reads an input, like an English phrase, and generates a vector representation of it. The decoder generates the output sequence over the course of repeated queries. As input, it uses the encoder's output, and the sequence of words that is generated so far. We'll break down the structure of Transformer over the next few minutes. I want to address some of the most important parts: the embedding layer, the use of self-attention, and the attention between the encoder and decoder. First, I'll talk about why it's so important that Transformer uses embeddings. Whenever we want to feed a word or a sequence of words into a neural network, we have to express the words as vectors. One simple way to turn words into vectors is to use a one-hot encoding, where the dimension of the vectors is equal to the size of our vocabulary. But this makes the vectors very large and very sparse, which can make learning difficult. In a way, the one-hot encoding is a way of turning words into vectors without assuming any relationship between the words, since every vector is orthogonal to every other vector. But in fact, we know that even at the word level, language has a lot of structure. Some words are interchangeable, some words commonly compared with other words, and so on. So we should choose an encoding, or embedding, where the vectors actually reflect this. For example, consider the dot product between some fixed vector v and a variable vector x. There's a sense in which the dot product of two vectors is like a similarity score between those vectors. If x is at 90 degrees with v, then the dot product of v and x is 0. As they begin to point in the same direction, the dot product becomes positive. And when they point away from each other, the dot product becomes negative. If the vector v actually represents a word, say apples, then we can try to choose an embedding where words that have some relation to apples are pointing roughly in the same direction, and therefore have a large dot product, or similarity score. Words that are decidedly unrelated to apples should be pointing away from it. In the paper, the authors used an embedding that had been pre-trained for general natural language tasks. Next, we'll look at self-attention. In natural language processing, a common practice is to filter sentences by removing what are called stop words. These are words like the, of, an, basically any words that don't add any real content. This kind of approach is a bit arbitrary because you just have to decide ahead of time which words are considered unimportant. But wouldn't it be better to model the relative importance of words in a sentence in a more continuous way? Self-attention does this by leveraging our embedding from before. Take this sentence for example, and suppose the embedding looks something like this. The goal is to re-represent each word by taking into account the similarity it has with other words. We'll focus on the word eat in this example. In the paper, the authors first project the vectors onto various subspaces, which are learned during training. Each subspace is referred to as an attention head. By computing dot products, we can see which words are similar to eat. We can re-represent the word eat by taking a linear combination of all the words, weighted by their similarity to eat. In the paper, the actual coefficients used were softmaxed values of the dot products, which had been scaled by 1 over square root of the dimension of the vectors. This process is done for each attention head, which can all be done in parallel. The speed of this computation is a big part of what makes attention valuable. All the new word vector representations are then concatenated together to be passed on to the next layer. The attention between the encoder and decoder is very similar to what I just described. The only difference is that the fixed yellow vector of focus will be a word vector that the decoder has generated previously, and other vectors are outputs of the encoder. In some sense, we can still think of these other vectors as representing the original input words. It's just that they've gone through a transformation in the self-attention layers. In addition, the yellow vector itself no longer appears in the linear combination. The intuition behind this process is that the French word vector j'aime provides information about the current context of what we're producing. We compute dot products with the inputs to determine which inputs are actually related to the current context. It's worth mentioning why we would bother using multiple attention heads, instead of just using the original embedding space as the only attention head. The main reason is that it's a way of getting to compute things in parallel. As long as the subspaces are good enough, we get a boosting effect when we combine the findings of each attention head. Well, that covers what I wanted to talk about in this video. Unfortunately, there isn't enough time to describe other features of the transformer architecture that are very important, like the positional encoding, which is how Transformer sees the order of words in a sequence, and the fact that the path length between any two input words is much shorter in this architecture than in an RNN. Anyway, I hope you found this video helpful for understanding the main idea behind Transformer.